Good day. Welcome to CMPUT 175. We are talking about sorting. And we saw a few algorithms like the bubble sort, the selection sort, the insertion sort. We were trying to improve. But we found them all to be in the order of n squared. And we ask ourselves, can we do better? Well, this is what we will see today. Mergesort is such an algorithm. It receives a container that is not sorted, or we don't know actually, and then the output is that same container with the elements sorted. And we will do it faster than order of n squared. Just to give you an idea about the process we'll go through, imagine that the students wrote an exam, the midterm one, but on paper, not online like we're doing it this semester. After we mark all these exams, I take them to my office and students come to pick them up because they want to see their grades and where they made mistakes and things like that. So to accelerate the process, when they come and knock at my door and say, I want my exam, what is your student ID? And I have to search sequentially, it takes too long. So instead, I spend the time sorting them, and then they can come and tell me their student ID, and I can do a binary search. Remember the chapter on binary search? It's way faster. Now, after a few weeks, I still have a leftover of midterm one. They're all sorted. Not everybody came to pick up their exams. And then we have the second exam, midterm 2. And I'll do the same thing. I sort them, then I have 2 piles. When the students come and they say, oh, I would like my midterm 2, I'll do a binary search and I'll find their midterm 2. And they may say, oh, by the way, I didn't come to pick up my midterm 1. Can I get it as well? Well, then I have to do a second binary search to find them. I'd like to do just one binary search and find them both. So the way to do that is to have just one pile of midterm 1 and midterm 2 all sorted. Well, I could just put them together and sort them again, but sorting takes such a long time, it's not the right solution. Knowing that both are sorted, I can simply merge them. I can merge them to create a pile that is already sorted. That is actually trivial. I'll look at the one on this pile, the one on this one, which one is smaller, and I'll put it there. Which one is smaller, this one, and so forth. I can merge them and keep them sorted. And this simple process is actually giving us an idea for sorting in general. What is the idea? Well, imagine those 2 piles were not sorted. If I had an oracle, some magic that says, boom, there you go, they are sorted. Now I can sort the whole thing by merging them. That's an interesting idea, except that we don't have this oracle that can do it by magic. We have to sort them ourselves. We could do that recursively. Each time I have a container, divide by 2, and somehow if this is sorted and this is sorted, I will merge them. But that is not sorted, so I have to do it again recursively, cut it into 2. If each side is sorted, I'll merge them, and so forth. So keep that in mind, and we'll get back to it. So the merge sort is basically a new algorithm that is not order of n squared, and we'll see that. So all the other algorithms we saw, bubble sort, selection sort, insertion sort, are all in the order of n squared. This is in terms of number of comparisons that they have to do, not in terms of the swaps or the shifting, because that depends upon the state of the container, if things are almost sorted or not. But in terms of the number of comparisons that we have to do, it's in the order of n squared. So we can do this recursion instead, where if we have a container, if I split it into 2 halves, and if I somehow recursively sort the left-hand side and sort the right-hand side, once they're sorted, I can simply merge them and I get a sorted list. Okay, so here's an example. I have a container, and you can see that the numbers are not sorted. These are the indices. I can split it right in the middle, and I get two sublists, the left-hand side and the right-hand side, and both of them are not sorted. The day they are sorted, I can merge them and sort this whole container, but they're not. So I'll have to divide them by 2, divide by 2, divide by 2, divide by 2. Eventually, I only have lists of one element. You see, it's like the tree here, and these are the leaf nodes. And when I have only one element, it's already sorted. I don't have to do anything. I'll do the same thing here. Divide by 2, divide by 2, divide by 2, divide by 2. So if I keep only those singleton elements, the leaf nodes, remove everything else. So this is my list. It's divided into one element each. Each one of them is sorted because there's nobody bigger than it, so 60, in that list containing only 60. There's nothing smaller than 60 and nothing bigger than 60, so it is sorted. So what I'll do now is start merging them. I'll merge the 60 and the 80. I'll merge the 60 and the 80 and the 50. Now I'll merge the 30 and the 70. And now I'll merge the 30, 70 and the 55, 60, 80. Wow, I got that sublist, the right-hand side, sorted. I can do it the same way on the left-hand side, the 95 and the 75, it's sorted. Now I'll merge the 10 with the 75 and 95. And now I'll merge the 25 and the 50. And now the 25, 50, 10, 75, 95. Et voila, now I have both sublists sorted. I can continue and merge, and I get my whole container sorted. That's the power and the beauty of recursion. It's very elegant. Now, how does this merge happen? I just showed you, boom, we merge. Well, the merge, and this is one of the, let's say, negative side of the merge sort. If I go back here, remember the bubble sort, bubble sort, selection sort, and insertion sort. We had the container and we shifted things around, or we swapped them, or we shifted them. We stayed in the same container. Okay, we call these algorithms in-place sorting. I sort in the same container. However, this merge sort, because I need to merge, well, it's not in place. So for example, if I focus on this 25, 50, 10, 75, 95, how do I do the merge? Well, I look at this list here, and I look at this list on the other side and see in the beginning who's the smallest one. Oh, it's 10. 10, I'll put it copied here, and then 25 copied here, and then 50 copied here. This one is finished. I take the 75, 95, put them here. So I had to put them in a different place. That will require additional space, additional memory. Then I will copy them back to the original container. You remember those exams? Well, it's the same thing. If I had a basket, let's have it here, a black basket here with midterm 1, and a red basket with midterm 2, when I merge them, well, I need another basket. I can't merge them in the red basket or the black basket because those baskets contain already midterm 2 and midterm 1. So midterm 2 and 1 sorted together will be in another basket. Then I will copy it back to the original database, container. So if I go back to this example here and explain it with the baskets, so basically in the first black basket I had the 25 and the 50, and the red basket I had the 10, 75, 95. When I merge them, I end up in the green basket. And then from the green basket, I have to copy it back to the original space. Well, this one is 2 spots. Here is 3 spots. So basically I need to have 5 spots here, and that's what the 5 spots are here, represented by the black and the red, basically these two put together. Okay, so when I'm merging, I can't merge in place. I have to merge in another space. Okay, so the 10 will have to be copied here, the 40 will be copied here, then the 50 will be copied here, then the 60 will be copied here, and then those 3 will be copied at the end. The size of the result is the sum of the size of the, let's call it left-hand side, and the size of the right-hand side. Because all these elements have to fit in the result. So the algorithm to do this is actually relatively simple. My input is left and right, two containers, and my output is one container that we'll call result. Okay. The left-hand side will be in increasing order, the right-hand side will also be in increasing order, and I need to have them sorted in order to be able to do the merge. I cannot merge two containers if one of the containers is not sorted, so both have to be sorted. It's extremely important. The size of result is the size of the left plus the size of the right, because every single element of left and every single element of right have to fit in result. So if result is of size n, let's call the size of the left n left and the size of right n right. Okay. So how do we do this merger? Basically, I will have three references to an index that is traversing left and right and result. All of them will be initialized at 0. So the current position in result is where I'll put my elements. And then I have, let's call them L and R for the pointers, or I and J, doesn't matter, references within left and right. I will repeat. What do I repeat? I'll check the current element in left and the current element in right, who's the smallest. And the smallest one will be copied in result. And then in the container where I copied from, I'll move forward by 1. In result, I also move forward by 1. Okay? And then at the end, how do I finish? I'll finish when one of the two containers, either left or right, will finish. And then I may have some more in the other container. Well, I'll copy the remaining elements of the other container into result. Okay? For example, if I have in left 1, 3, 5, 7, 9, and in right I have 2, 4, 6, well, I'll copy, I'll compare 1 and 2. 1 is smaller, I'll put 1 here in the result, and then 2 and 3, well, 2 I'll put it here, and I move forward into 4. 4 and 3, well, 3 is smaller, and I move forward here, so 5 and 4, well, 4 is smaller, and then I move forward. 6 and 5, well, 5 is smaller, and then, well, move forward here. 7 and 6 was smaller. Well, 6 is smaller. I'll put it here. Well, right is finished. I cover them all, and therefore I'll take 7 and 9 and copy them here, and you can see result is sorted. Left was sorted, right was sorted, and result is now sorted. Let's see another example. Here I have a container, we'll call it left, and a container which is called right, and this is the result, and the result in the beginning is empty. My current is at position 0, current of the right is at position 0, and the current of the left is at position 0. I'm indicating them with red to say that's the current element. I will compare 10 and 50. Who's the smallest? Well, 10 is the smallest. So I will copy 10 in the result, and I'll move forward in left. And now I compare the current is 40, and the current here is 50. I'll compare them. Who's the smallest? Well, 40 is the smallest, and therefore I will copy 40 here, and I'll move forward in left. Now I compare the current in left and the current in right. Who's the smallest? Well, the current in right, and I'll copy 50 here, okay, and I move forward in right. Now I compare against 60 and 70. Who's the smallest? Well, 60 is smallest, therefore I will copy 60. I move forward. Oops, I finished my left container. So what I do, I will copy from the current position of the right hand side till the end. I'll copy it here, and there you go. I finished the two containers, and I obtained a merge of the left and right in one container called result. So let's see well, we talked about the algorithm. Let's see the code. We can write it as an algorithm, then compare code it, but let's do it directly in Python here. The merge has left and right as input and will return the result. As you can see, return the result. So in the beginning, the result is, there's nothing there. I start with an empty list, and I have I and J, the current references, a reference to the current element in left and right, and I start at 0 for both of them. Okay, while I is smaller than the length of left, so I haven't traversed the whole left, and j is smaller than the length of right, I haven't traversed the right yet, I compare the current to the left and the current to the right. If left is smaller, then left is appended to a result, and I move forward in with I is equal to I plus 1. Else, it means actually it's the opposite. Then I will append the right of j in result, and I move forward with j. J is equal to j plus 1. Once I finish this loop, what kicks me out of this loop? Well, either I finish the left or I finish the right. One of them. So what do I have to do? I have to copy the remaining elements in the other container that is not finished yet. Well, this is how I do it. I take the left from I till the end, and I append it to result. And I also append to results the right from j till the end. Why am I doing them both? We said only one of them will finish. Well, it doesn't really matter in this case. I could have a condition. If I is still smaller than the length of left, then copy the remainder of left. Otherwise, copy the remainder of right. But without even making a test, we'll do them both. One of them will be empty. It means actually that instruction will not do anything because I till the end, well, I is already at the end in case left was finished, and same thing with the right. So only one of these two instructions will have an impact on result, and then I return result. Okay, so this is merge, it's not the sort. I haven't sorted anything yet. I received left and right sorted, and I merged them. So how do I sort? Well, I'll sort with a recursive call. Merge sort receives data as a reference to a container containing the data that I need to sort. And if data, the length of data is only 1, so I have only one element, well, it's already sorted. I return that data. Otherwise, I have more than one. In that case, I have to cut it into 2. Where do I cut it into 2? I go right to the middle. How do I get the middle? Well, the length of the data, integer division by 2. I'll get the middle. Now, I will sort the data from the beginning to middle, and I will call it recursively merge sort, the same function. I have a parentheses missing here, closing and closing. So the merge sort of the data from the beginning to middle, that becomes my left. It'll be sorted. And I will merge sort the data from the middle till the end, and that will be right. So if left and right are sorted, I'll just merge them with the algorithm that we just saw, and that's what I will return. Okay, so what is merge sort? It's this merge sort. We'll keep on calling recursively until I have the base case. So why is this recursion working? Because I have a base case, and I'm simplifying my problem towards the base case, because each time I'm calling it with half of the data. Okay. Now, does this work fast enough? Is it order of n squared, or something else? Well, let's compare it first. And since we have the implementation, I'll compare it with, let's say, selection sort. Okay. So here's merge sort, here's selection sort, and I'm calling them with a large container of 20,000 and 100,000 elements that I need to sort. Well, merge sort takes less than a second to sort 20,000 elements, while selection sort takes 16 seconds. So big, big difference. For 100,000 elements, merge sort does it in 1 second, while selection sort 400 seconds. So definitely merge sort is way, way faster. But how fast? How many comparisons are we doing? Well, we have a container, and we recursively cut it into half, cut it into half, cut it into half, cut it into half. So it's very similar to this idea of the binary search. How many times did I divide my container till I reach the base case? What is the base case? It's one element. So I have a container of n. How many times I have to divide by 2 till I reach 1? Well, that's the definition of logarithm base 2 of n. So the number of divisions is logarithm base 2 of n. But the algorithm, merge sort, doesn't just divide by 2. It does the merge as well. So there are two actions that we have to do is the division, but then I have to merge. How many times I have to merge? Well, or how many do I have to merge, not how many times. Well, in every single level in that tree, I have to eventually merge every single one. Every single element has to be compared to decide whether I put it from the left or I put it from the right. So in each level I have n comparisons. And how many levels do I have? I have log base 2 of n. So it's n log n, the complexity of the merge sort. So n log n is approximate, it's the order of the number of comparisons that we are doing in order to finally sort this container. So it's actually quite fast because log n is very small compared to n. We had n times n squared, now we have n times log n. Way better. We love that. But there is a problem. In the selection sort, bubble sort, and insertion sort, they were all n squared, but I was doing just shifting or swapping, and I did it in the same container. The only additional data that I need, space that I need, is this additional local variable called temp, where I put it temporarily to move it somewhere else. That's the empty bucket that I used to swap paints from different buckets, if you remember that slide. So basically, the space complexity for those algorithms was in the order of n, just the container. Here, because I need that green basket, I need extra space. How much extra space? Well, I need n. So my space complexity, in order to do the merge sort, because of the merge, is 2 times n. N, the original container, and another n to do the merge and then copy them back. So yes, we have a very efficient algorithm in terms of comparisons, but it requires additional data. If we have a lot of space, if we have a lot of space, it's not a big deal, but doubling the space is typically bad. So we love the n log n time complexity. We don't like the space complexity. Can we do better? Again, that's the question we always ask. Can we do better? Well, in other words, can I use n log n and stay in place? There is a way. There is a way, and this is what we'll see in quicksort. And the idea is to find some element in that array, in that container, we'll call it pivot, and we'll put the pivot in its right place in such a way that all the elements on the left-hand side are smaller than it, and all the elements on the right-hand side are bigger than it. And if I can do that, and I can do it recursively again and again, then I will sort the table. And this recursion will allow me to get the n log n, and I'm doing it in place. So that's the high-level idea. I'll explain it in the next lecture. So thank you for your attention, and think about that. How do I find an element, put it in the right place, and make sure that everybody on the right-hand side is bigger than it and everybody on the left-hand side is smaller than it? Okay. And if I can do that, we get quick